Hey, AP students, welcome to first lesson in acid and base chemistry. We're going to just kind of do the basics today, describe a couple things that are going on. We'll also talk about the lab that you guys are going to do, the first acid-base lab anyway, with the standardization of NaOH. But let's go ahead and get started and see where we are. So one of the first things I want to talk to you about is you guys have a bonus opportunity. I'm not sure if your instructor has discussed this with you or not, but you guys will have a bonus opportunity. Oh, this is kind of, there it goes. Bonus opportunity with to make Valentines. So you did this in advanced chem or pre-AP last year, but you can make up to 2 Valentines, 10 mole bucks each. They need to be extra corny, super, silly, hopefully, and hopefully also not off of Google. One of the things is wrong actually here on this PowerPoint. This shouldn't say Wednesday, February 7th. That's my bad. That should say Monday, February 7th. So this coming Monday, if you want to put together a couple of Valentines, I hope that they're not, you and I together kind of Valentines like up in the top left corner, but come up with your own. You guys are in AP Chem, you know a lot of chem, you should be able to come up with a decent Valentine without using the Google as your source. Okay, enough about that. So what we're going to talk about in this first video for acids and bases, we're just going to discuss the general nature of acids and bases. We're going to identify which ones are acids, bases, and use 3 different definitions to identify what those things are. And you may remember them from last year, Arrhenius, Bronsted-Lowry, and Lewis acid-base theory. We didn't really cover Lewis too much, and I'll discuss that when we get there. But yeah, we'll just revisit the same ones we did last year, kind of in the same depth. So anyway, nature of acids and bases, and just fill your notes out as you go along. If you need to press pause, press pause. I realize that I go a little faster, some of the other instructors, but that's okay. Nature of acids and bases. So acids are going to taste sour generally, like lemon juice or lime juice. They're going to have pH values, if we tested them, that are going to be less than 7. They can be as low as 0.1. Heck, they could even be negative, but they're definitely going to be less than 7. Typically, they have a hydrogen in front of the formula, so you'll see something like HCl, hydrochloric acid. That would be an acid. H2SO4, another easy example, sulfuric acid, that's an acid. So they generally begin with hydrogen. Some of the easier ones, some could be drawn differently though. You might see like acetic acid written CH3COOH. That is a carboxylic acid, and the hydrogen at the very end is actually the dissociative hydrogen. But okay, we also write it as HC2H3O2. So it's not sort of an all-inclusive thing, like everything that starts with H is an acid, but most of them do. I do know you're familiar with H2O. Water can have acidic and basic properties. The pH, of course, of distilled water or of just pure water is 7. So it's neither an acid nor a base, really. But given certain circumstances, it might be more of an acid than something else, or it might release hydrogen ions in a certain solution and behave like an acid. So typically they'll have a hydrogen in front of them, but not always. Bases, though, bases are referred to as what we call alkali or alkaline. If it's alkaline, it means it has basic properties. They taste bitter and feel slippery. Soap is a base. If you've ever had your mouth washed out with soap, I know my children have. It kind of tastes bitter and it has that slippery feel to it. They have pH values that are greater than 7, and usually they have a hydroxide in the formula. It says at the back of the formula, which is true. But yeah, sodium hydroxide is NaOH. So the OH is its basic, or tends to be why it's a base. There are other bases, like ammonia is a base. Ammonia does not have a hydroxide in it. So again, we're just saying, generally speaking, they have hydroxides in them. We're going to say that the strong ones have hydroxide in them, and even though that's not entirely true, but it's pretty close. And you know how it is in AP Chem. We're gonna get as close as we can to what it really is and kind of move on. So yeah, they'll have a hydroxide in the formula. So there's three general definitions, like I spoke to earlier, about acids and bases. And the first one is the Arrhenius. So the Arrhenius acid-base theory says that acids produce hydrogen ions in solution and bases produce hydroxide ions in solution. Now, this does not cover all acids and bases. You know, all acids don't necessarily produce hydrogen ions in solution, but the majority, like, 90+%, 99% do. But there are other things that have acidic properties, maybe cause something else to lose hydrogen ions or produce hydrogen ions in solution, but don't actually dissociate those hydrogen ions. But the Arrhenius definition is the first and most basic. It just says acids make hydrogen, bases give off hydroxide, and that's it. HCl and NaOH here are great examples of this Arrhenius concept. Hydrochloric acid will give off H+, and NaOH will give off hydroxides. This doesn't tell you whether it's going to be strong or weak. This just simply tells you whether yes or no it's an acid or a base. So a more complex or a better definition, and the one that we'll use 99% of the time, is Bronsted-Lowry model. Bronsted says that you're giving off protons. So acids are H+ donors or proton donors. That is the same definition as Arrhenius. They also say, or the definition also says, that the donors, if they are bases, are proton acceptors. So in other words, they accept the hydrogen ion rather than giving off hydroxide ions. Now, it may be that hydroxide ions are given off kind of in conjunction perhaps, but here what we're talking about is that they're accepting a proton. So if you did ammonia, for example, ammonia would accept a hydrogen ion from water and become NH4+. That's an example of a Bronsted-Lowry acid-base scenario, or a Bronsted-Lowry base anyway. And it accepted a proton. Now, it did release hydroxide ion solution by taking one from the water, but nevertheless, it didn't dissociate to give hydroxide ions. In these, when we do this, you do need to know that hydronium and hydrogen, or hydronium and protons, are going to be used interchangeably because most of this is in aqueous solution and we just leave water out. But if you want to write H3O+, you're going to see it both ways. More often than not, if I'm your instructor, I'm just going to use hydrogen ions. It's just faster. I'll just dissociate hydrochloric acid at H+ and Cl-. I'm not worried that it's reacting with the water to perform to produce H3O+. But know that those are used interchangeably, and so you're going to see both. Some people prefer hydronium over hydrogen ions in your formulas, but I prefer the hydrogen. It's just faster. So here, if I have an acid and a base, if an acid reacts in water, I should say, it'll give off hydrogen ions. I could have written this as H+ and A-, but to demonstrate what's happening here, I'm going to show that the hydrogen is actually being accepted by this water. That makes it a base, a hydrogen ion acceptor. And the HA, the acid, is going to lose the hydrogen to become its conjugate base, A-. With Bronsted-Lowry theory, it's really conjugate acid-base theory as well. So what you're doing is you're producing a base from an acid, which we call the conjugate base. And so you see that happening here, the acid becoming its conjugate base. And the conjugate acid is being formed from the base as it gains the hydrogen ion. So the base becomes a conjugate acid. You will have to label things as acid base and conjugate acid base. Now, it doesn't necessarily matter that there's, an equilibrium arrow in the middle here, that it shifts back, right, forward and backwards. That doesn't really make any difference. It's still considered conjugate acid base theory, even if it goes to completion. But we'll do some things with the conjugate acid and conjugate bases in the future. And we may be moving reactions and flipping them depending on what we have present at a certain point, say in our reaction, where we're not at equilibrium and it shifts back to another side. So just be aware that we're going to kind of use this the whole time. Your acid and bases are going to be on your reactant side. Your conjugates are always going to be the things that are produced. Regardless if you're going in a reverse direction, we're still going to say the acid and base are on your reactant side, and the conjugates, of course, are your products. Okay. So here, the last definition that we're going to use is the Lewis model. Lewis, we really don't use in AP chemistry. There's a kind of a movement away from using it, even though it explains acid and base theory perfectly. Things that accept electron pairs are going to be acids, and things that donate electron pairs are going to be bases. So if you look at the example here with boron trifluoride and ammonia, the ammonia is actually donating this pair of electrons here to make a coordinate covalent bond. And at that point, it's lost its basic nature, and BF3 has accepted that hydrogen, that pair of electrons, losing its acidic nature. So BF3 in this case would be the acid, and ammonia, of course, would be this base. This does actually change the pH of solutions, but it is something that is a little beyond the scope of what we're going to talk about, but you do need to know the definition of it. Do be able to identify which one is the acid and the base if you're given a reaction in which a pair of electrons is donated and accepted. So yeah, just flying through stuff here. The acid dissociation constant is the same as what we used in equilibrium. So the equilibrium constant is KEQ, right? You could have called it a concentration. So you could have called it Kc. You could have called it, or we could call it in the future, Kw for water. None of these make any difference. They're all calculated the same way. So what they are is they are the product concentrations divided by the reactant concentrations, leaving out your solids and your liquids. In a lot of cases, there's going to be water in these situations. Water is a liquid. It is the solvent. And so it is actually left out of the expressions. Now, if you see H3O plus, remember that that is the same thing as H plus. So we're not really losing, that is not water. H3O plus is not the same thing as water. But what's missing down here in this is actually the water, but we've left it out because it is a liquid. It is the solvent in this case. Even though you don't see all the elements present in the Ka value, that doesn't really make any difference. The one on the bottom is the way I would write it, leaving out the water so that you don't get kind of confused, but it doesn't really matter. If the water was present, you would just leave it out because it's an equilibrium expression. So we'll use the A to signify that they're acid dissociation constants. These values will be for strong acids and stuff, they're going to be really high, meaning they push to make a lot of products. For weak ones, they'll be very low. They'll be less than 1, meaning they favor reactants. But it is exactly the same as our equilibrium concentration stuff. So the amount of conjugate acid base formed from the exchange is going to be shown by this equilibrium constant expression, and you'll be able to compare K values for different acids to find out which ones are stronger or weaker. Same thing with bases. So the large Ka value indicates that you have more product present. Remember that equilibrium constant expressions, be it Ka, Kc, Keq, doesn't matter. In this case, Ka, it's going to be your products over your reactants, right? So it's going to be your conjugates divided by your original acid and base, or in this case, acids. And so what you'll have is a number that would be greater than 1. And some of these K values are crazy high, like millions or whatever. Those are going to favor products. A small Ka, meaning one that's less than 1, means that it's going to favor the reactants, just like we had before. If it does favor the reactants and not the products, it means it doesn't dissociate very much. If that's true, we call those weak acids. If they dissociate a great deal, we call those strong acids. And in order to know which one's which without a Ka value, you'll have to memorize them. And so we'll have you guys memorize some of this stuff. So here's kind of an example showing you, there's little graphs, little bar graphs on the bottom, but if you have a strong acid, it really is more appropriate or most appropriate to write this as a single arrow in one direction. So what happens is it produces all hydrogen and the conjugate base A minus here, where if you look at this other one, this really should have been written with, oh, I guess those really aren't products, are they? They're showing you what you have at the end. That's silly. But if you were drawing this, you actually would have a reversible arrow in a weak acid formula. But that's okay. So here what they're showing is that the HB breaks up, but it doesn't break up entirely. You still have quite a bit of it left. So I guess if I'm being all super perfect here, this would actually be kind of a double-sided arrow here between your reactant, the HB, that weak acid, and then producing just a little bit of the hydrogen and the conjugate base B minus. And so there you go. Those are weak acids on the right-hand side, not very much dissociating. If you notice, there's just a single dissociation here, whereas on the other one, the entire thing is dissociating. Strong acids will dissociate completely, and weak bases will dissociate partially. And that'll be obvious from what their K values are because they'll be small if they're weak. So mostly dissociated are going to be your strong ones. There, yeah, showing it's completely dissociated into H plus and A minus. The equilibrium lies far to the right. You wouldn't, if you add more hydrogen ions, it's not going to go back and produce more acidic solution, or sorry, it is going to produce more acidic solution, but it's not going to shift back to the reactant side. This is really not an equilibrium. However, with weak acids, it is. Strong acids is going to yield that weak conjugate base that I said. That weak conjugate base is actually weaker than water. We'll talk more about that later when we do kind of acid-base equilibria, but for now, we'll kind of leave that alone. So common strong acids, there are 8, and you need to memorize them. They are sulfuric, nitric, perchloric, chromic, permanganic, hydrochloric, hydroiodic, and hydrobromic. If you look at the ones on the right, you'll notice, well, you notice a couple of things about both columns, I guess. The ones on the right are all hydrohalic acids, meaning they have halogens, right? Hydrochloric, hydroiodic, hydrobromic. You'll notice that HF is not there. HF is actually a weak acid, and we'll discuss it in a minute. But it is not strong, even though it has crazy properties as an acid, and it can be used to dissolve all kinds of different things, which which I won't discuss today. But yeah, it's not considered a strong acid. It has a low Ka value. Well, it has, yeah, it's a Ka value is less than 1. If you look over on the left, what do you notice about kind of all those? What do all of those have that the other ones don't have? They have a lot of oxygens. And so we'll talk about this too, about oxyacids, but substances that have a great deal of oxygens tend to be really strong. Now, phosphoric acid is not on that list, but phosphoric acid is pretty nasty stuff too. It is, however, it's weak. It's a weak acid, but it has some, like I said, some interesting properties. But here, those are going to be the list of strong acids that you need to know, all 8 of them. And you will assume that these are going to dissociate the first hydrogen on each one of them 100%. So 100% dissociation of the first hydrogen. And by first hydrogen, I'll also discuss that with you later too. And I know you're excited. We'll do some Rice tables that demonstrate their weak nature after the first dissociation. So weak acids, like I said, mostly undissociated. So you're going to have the majority of the acids still present. This is the same graphic from before. It's going to favor the reactant side. So you're seeing that single dissociation from your original reactant. So just a little bit. Acetic acid is like that. Vinegar is a weak acid. It's the one we typically always use. So yeah, weak acids just not dissociated very much. They will have a stronger conjugate base than water, but we'll deal with that again later when we get to that point. So yeah, if you put strong acid in there, you're going to have something that is actually going to give off quite a bit of hydrogen ions. It's going to change the pH a lot. Whereas with weak acids, you're not going to have very much, not a great deal of change in the hydrogen ions or the pH. If you look at the relative acid strength relative to conjugate base strength, this is interesting. Things that are very strong acids are going to have really weak conjugate bases. Their conjugate bases aren't going to be very strong at all. They don't favor switching to the other side. There's no movement back to the reactant side. There's no shift in equilibrium really. They just produce conjugate bases that are incredibly weak. If you look at very weak acids, they actually have conjugate bases that shift back to the other side. So they're going to be relatively strong. That doesn't mean that their Kb values are extraordinarily high, or it makes them a strong base necessarily. It just makes them a stronger base than water. And again, we'll discuss more of that later. So sulfuric acid is diprotic, which means that it gives off 2 hydrogen ions. And this graphic is actually quite wrong. This should not be an equilibrium arrow. It should be to completion arrow, a single-sided arrow. H2SO4 will give off a hydrogen ion 100% straight away. Its conjugate base, which is bisulfate or hydrogen sulfate, also has acidic properties, meaning it gives off a hydrogen too, but it doesn't give off the hydrogen as easily as does H2SO4. Part of it is that hydrogen that is already dissociated is pushing the equilibrium back, and we'll show you that later too. But it's also the fact that there's a stronger attraction for that hydrogen than there was for both of them when they were there. And so it will have a Ka value associated with the bottom one that is less than 1. The top one, it's really not appropriate to say it has a Ka value because that value is so much greater than one that that it's just too large to even kind of comprehend. So we just say that it's 100% product. You'll also see that the oxy acids get stronger as they have more oxygens on them. So if you were to look at, sulfurous acid versus sulfuric acid, sulfurous is H2SO3, sulfuric is H2SO4. What happens is those oxygens actually pull the electrons towards them away from the bond with the hydrogen. I'm doing that up there, pulling them away and making it easier to dissociate, sort of a more polar covalent bond. And so it dissociates it very easy. There are some weaker oxy acids like phosphoric and nitrous and sulfurous too. Those are not going to be strong, but they're stronger than those that don't have the oxygens. Within a series, if you have the same ones, so like HClO4, you have the same counterpart to the oxygen, so HCl. If you had HClO4, it's going to be stronger than HClO3, which is going to be stronger than HClO2, which is of course stronger than hypochlorite. So hypochlorous acid. So the more oxygens, the more they pull those electrons out of that bond and make it more dissociative and actually stronger. The last one are organic acids. Organic acids are going to have a COOH group. That COOH group looks like this. And because of those oxygens pulling those electrons towards them, it's going to make that bond right here with that hydrogen relatively easy to dissociate, I should say. And so you'll see a lot of these will have acidic properties. And so we call this a carboxylic acid group or organic acid group. You'll see that in acetic acid, formic acid, benzoic acid. Anything with oic acid at the end is going to be an organic acid. And then I said the last one last time. This is really the last one. Our hydrohalix. Remember that I said that HF was actually weak? The HF bond is crazy polar, 4.1 and 4.0 and 2.1 for their electronegativity. So 1.9 difference of electronegativity is actually quite large. You would think that it would dissociate entirely, but it doesn't because due to the small fluoride atom, or fluorine atom if you prefer, the fluorine atom, it's so small and hydrogen is so small that the Coulombic attraction is strong because the denominator of Coulomb's law is actually really small. So you have a very, very small distance between them. And so it has a really strong attraction between the hydrogen and the fluorine. That is not true for chlorine, iodine, and bromine. Those three would actually make stronger acids. So the electronegativity does make a difference. But for the most part, even though HF is stronger, it doesn't make a difference. It's just the size of it actually plays a greater part than does the difference of polarity or electronegativity. However, for HCl, HBr, and HI, it does. And also the distance between those is getting farther apart, denominator of Coulomb's law, actually making those stronger. In terms of electronegativity on the bottom one, if you're looking, these are actually, because of those, it's going to be stronger based on electronegativity. HF is just an exception in this regard because of its size. Let's see, where do I need to go here? I'm going to pause and come back. Sorry, guys. So some substances have the ability to both gain and lose protons. Those substances are called amphoteric or amphiprotic, but amphoteric substances. Water is a perfect example. So water can gain hydrogen ions and water can lose hydrogen ions. When it gains hydrogen ions, it becomes H3O plus. When it loses hydrogen ions, it becomes hydroxide. This is not the only substance that does that. Dihydrogen phosphate does it. Bicarbonate does it. Bisulfite does it. Bisulfate does it. They can gain hydrogens and produce their original acid generally, or they could lose hydrogens and become the other. So if you're looking down at the bottom, it's dihydrogen phosphate is this example down here, where you have the ion dihydrogen phosphate or H2PO4. Oh, sorry, this would be H2PO4. H2PO4 minus can actually gain a hydrogen ion and produce the phosphoric acid, or it can lose an additional hydrogen ion and then become hydrogen phosphate or just biphosphate. So it has acidic properties and basic properties. And so we call that substance that can do that. And it's in different circumstances depending on what it's exposed to. If it's exposed to an acid, it'll behave like a base. If it's exposed to a base, it will behave like an acid. And so those substances that do that are called amphoteric substances. Just something, just a little definition for you. Yeah, the auto-ionization of water is also a perfect example. So I briefly want to talk about the lab that you guys are going to do. Some are going to do it tomorrow. Others are going to do it on Monday or a couple days from now. But I did want to just kind of briefly tell you what you're getting yourself into. And it's going to be a 2-day lab. So what we're going to do is you guys are going to be given a weak acid, which is potassium hydrogen phthalate, or KHP. And you'll also be given a 1 liter flask. And what we're going to ask you to do is to dilute 6 molar sodium hydroxide to 0.1 molar approximately. But we want you to get the exact molarity of that. So what that's called is standardization. And so you're going to standardize your sodium hydroxide against a known amount of acid. And in this case, our known amount of acid is going to be of that KHP. So this is kind of a little thing showing you, you guys need to bring with you a 1 liter bottle to school, empty, hopefully. So an old water bottle or whatever. That's not a 2 liter, a giant bottle. It's a 1 liter bottle, and I don't have one to show you. That was foolish. But a 1 liter bottle you'll need to bring to school so you can actually store your 0.1 molar, or approximately 0.1 molar sodium hydroxide, because we're going to use it for, oh gosh, the next 3 labs. And then your sodium hydroxide that you have, I want back when we finish, because we need some 0.1 molar for pre-AP, and I'm kind of using you guys. And it's good for you because if you do a large dilution, you'll be more accurate. But we need some acid, we need some base rather for the titrations for on level and advanced. Anyway, so you guys will get a volumetric flask, and you'll have graduated pipettes by the sodium hydroxide in the back. It will be 6 molar. And it says here, recap, I underline this, recap the NaOH containers. Sodium hydroxide is hygroscopic, so it grabs water from the surroundings and it'll change its own concentration. In fact, it'll dissolve itself with water vapor in the air and not stay as a solid. So you got to make sure that you put it away. That's one of the reasons why we have the KHP is kind of the same way. We'll have them inside desiccators. Mine look like flying saucers. I'm not sure what your instructors look like, but make sure that if you take it out of there, you put it back in the same fashion that you found it. You guys are going to do 3 titrations by the end of the period. Once you do your first titration, you'll be able to do this you'll be able to do the second, third one really quickly. But you'll be getting, excuse me, I think it's about 0.5 grams. I need to double check on the lab. I should have done that before I started the video. But I think you're getting, yeah, about 0.5 grams. It says between 0.5 and 0.6 grams of KHP from your desiccator. You can do that on an analytical balance. Keep all of your digits of that mass so that we can find precisely how many moles we have. And then that equivalence point where the phenolphthalein turns pink in our titration, the moles of acid, moles of base will be the same. You can then calculate what your concentration is of your base by taking those molarities and averaging them. You should have 1 for each of your 3 titrations, and then you just average the 3 of them. If you have questions, ask your instructor, but it's pretty straightforward. I did want to make sure I kind of told you what you're getting yourself into. This would definitely be a lab that'll take a little bit more time as you haven't titrated in a while. Some of you were gone last year and you digitally titrated during lockdown, and so that's not good. So we're hoping that this will go well. That's basically everything that I had to talk to you guys about that. Just be prepared to do some titrations. Okay. I'll see you guys in lesson 2, and we'll start taking apart some of these weak acids and maybe do some rice tables. Okay.